we're the acoustic calibration system for underwater acoustic transducers. My name is Diego Rochetti. I'm the team lead.
I'm Jesse Canale.
Matthew Aries.
And Kevin Costello.
So I'm going to begin with a quick overview of the project here, and I'll start off with explaining what a transducer is. It's basically, in its simplest form, a device that converts physical quantities into an electrical signal. And the customer that our customer's company creates underwater transducers, and those are used for applications such as underwater communication, object detection, so ships don't run into marine life. And these transducers need to ensure accurate data, so they need to be calibrated, and currently the method of calibration is very crude and outdated, so we've been tasked to update this calibration process. So the customer's requirement is to design a data acquisition unit to be able to send and receive signals and automate some of the measuring processes. The other requirement is to develop a graphical user interface that also, so we can see these signals transmitted, received, as well as do post-processing for the calculations. The engineering requirements, you can see there's some red here. The red indicates the updated requirements due to some discrepancies with the purchasing process between the company and the university. So our hardware was delayed, and we didn't receive the hardware until after our spring break, giving us only about 5 weeks worth of testing and development of the software there. So basic requirements included measuring the voltages and the current magnitudes, perform a frequency sweep, sample and reconstruct signals, control a rotational motor for one of the calibration measurements, plot signals, recall measurements, and generate a test report.
Okay, so as a little functional overview, as you can see on this right-hand side, it's a more simplified version to show the other aspects that this system could function as. So our two pieces of hardware will be interfacing with these acoustical signals to send and receive. Then on the left-hand side, this would be more of BTech's use of combining them with an amplifier to send and receive signals through transducers underwater. So these are our alternatives beforehand. We were debating on whether or not we would have to buy a pre-built computer or a custom built. And we figured it would have to have at least 16 gigabytes RAM, at least 500 gigabytes SSD or hard drive, and a relatively recent CPU. And for function generator, we were debating on buying an off-the-shelf function generator that would be able to interface with MATLAB so we can fully program it. We listed a couple models here, but this isn't something we ended up following through with. For the data acquisition unit, there's a couple specifications. This is more of a USB oscilloscope. It had to be sampled at max at 1 megahertz, and it would be ideal if it could do simultaneous sampling between channels. So for solved alternatives, we were able to kill 2 birds with 1 stone with most of the categories by choosing the 2 USB oscilloscopes, the Handyscope HS5 and the HS6. The HS5 has a unique feature where it also has a built-in function generator with 2 channels that can also read. For the HS6, it has 4 channels, and they can be coupled together via a coupling cable for a total combined 6 channels. For the computer, we just chose a pre-built laptop. It's a Lenovo ThinkPad T560, this laptop actually. And this was more for portability reasons. They could be transferred between the CIE building and the SMAS building to help with their calibration.
So I'm going to go over a little bit of the technical design that we had to overcome during this project. So the first thing that we had to do was build a MATLAB user interface, and this is definitely not an easy task. we learned about MATLAB throughout our years here, but we never actually used the app developer to develop such complex user interfaces. So this was definitely something that we had to overcome. But we have done other programming languages like C# and Python to develop UIs, but this MATLAB is much better for these pieces of equipment that we have, because they do have an SDK library in which we can communicate with them via the USB. Simultaneous generating and sampling was definitely something that they didn't even have a feature on their end of the TiPi hardware. This is something that we actually developed in our code. It was to be able to take a image of the oscilloscope while also sending it a signal. So what we would do is we would send both the signal and receive the data at almost instantaneous. We tried to get rid of any delay that was possible during that. Hardware communication, this was very easy for these pieces of hardware because it's USB, and we have the SDK libraries. The Arduino MATLAB communication, this was something that they had. The Arduino was code that was already written in their rotational devices. We had to actually convert this into MATLAB code in order to be able to control the rotational devices at the CIE building. Understanding transducers is definitely one of the biggest things, obviously, for this project. Understanding how transducers work, how we actually calibrate them, and it's basically taking a variety of different measurements and making sure that they're within the range of a calibrated transducer that we would use for reference. All right, so now we go into the test plan. So these were mentioned earlier, measured, transmitted, and received voltages. We were able to get both of these done. Frequency sweep method, this was something that they wanted in order to do different types of measurements, such as directivity beam patterns and things like that. We implemented this feature to be able to do multiple different transmitted signals at different frequencies, depending on the user's input. We'll show this later in our demonstration. Sampling, we got working correctly, being able to read the data. The rotational motor controls, we actually got that working just a week and a half ago. It was something that was last minute, but we got it all working and being able to go to the angles that you want to go to. Plot signals real time. Recall measurements, this is definitely one of the biggest features that we definitely want to show off, because you could save all your parameters within our user interface and be able to recall them within a click of a button, so you won't have to take a picture or have to write down the measurements that parameters that you're actually filling in. This feature makes it very easy for any person doing a calibration to be able to just go instant. Generating test reports, this is something that we also did with the state file. It will generate all the voltages that we are receiving into an Excel file, and I'll show you later on in the demo how that works. So the requirements that we did meet was the MATLAB user interface, which we were able to send, receive signals, save the data to an Excel file, implement the frequency sweep mode. We were also able to do gate signaling. This is something that's needed in order to get rid of the reflections that occur on the tank that we'll be doing our calibration in. Recalling measurements, he wanted this feature, and we got it to him. The rotator controller, we were able to display the start, move, and final degrees. The requirements that we did not meet were the calculations. So considering that we just got this hardware 5.5 weeks ago or so, we had to get rid of the calculations portion. But it's very easy for whoever is going into the next project to be able to use our data and put it into a script. Automate the frequency sweep with the rotator controls. This is something that he wanted with the rotational device, to be able to sweep through different frequencies and also take measurements. This is something which we think could definitely be implemented if we had a few more weeks, but because we got the hardware so late. Current impedance measurements and frequency versus voltage graphs are also things that weren't included, but we do think it's can be done. All right, these are just quick images. I'll go through these fast. Sorry, I'm keeping a lot. So this is our user interface that we had developed. So there's a bunch of different parameters for the function generator, settings, oscilloscope, sample, estimator, which will allow you to sample the amount of, estimate the amount of samples that you need to take in order to catch the received end of the signal. Use the gating, like I mentioned, the save settings, which you can save the file and all the parameters, trigger settings, just like a regular oscilloscope and a function generator. We've basically incorporated all this within one user interface. So on the second tab, we have this is going to be mostly for the frequency sweep settings for future work. Both of these do work. And the next step on top of this would be to just get the graph and be able to have it automate and take the facility. So, there we go.
Is there any way to put monitor higher or no? I see the projector.
Alright, just listen closely, I guess.
Alright, everyone. My name is Jim Short. CIE building demonstrating the transducer calibration. By hand here, we've got BT1201 transducer, which is produced by BTech. On the right side here, we've got an input wire, which will do that calibration. I'm going to place the transducer on the side of the tank after the line, which will receive the signal. About a meter away, we've got another BT1201 transducer, which will transmit the signal. Going over to the hardware setup, we've got the HS5 and the HS6 here. The output of the function generator will connect to channel 1 first to be able to see the signal. The output will also be coming from the amplifier. For our purposes, we're going to be setting a 10 volt peak to peak value, which will then go to the amplifier and do a gain times 7. So the output of the amplifier will have 70 volts peak to peak, which will then be connected to the transmitting transducer. Due to the attenuation through wire, we're going to be needing a preamplifier. So for the preamplifier, we're going to have 50 times gain, which will be connected to the amplifier. Preamplifier will clear the signal across the pin. We'll have the output connected to channel 2, on which we'll be able to see the receiving end of the signal. Now that we've got all the hardware set up, let's get started.
Hi, I'm Jesse, and I'm here to demonstrate the software for this calibration. Let's first connect to the device. We call a previous test from another calibration. As you can see, that automatically inputs the parameters from that test. Let's select channel 1 for the transmitted signal, channel 2 for the received signal. Select run. For this demonstration, let's go ahead and reduce the burst count and increase the number of samples. As you can see here, the blue represents the transmitted signal, the red represents the received signal, and we can see some backscatter from inside the tank. So let's go over here and demonstrate the gating feature. Let's go ahead and enable that, run, and we can see that the backscatter is eliminated. Let's go ahead and save this test. And open the test results. As we can see in this Excel spreadsheet, we have all the parameters input as well as the raw data used for post-processing.
Alright, so that's a demonstration for the CIE building, and that is our project.